IMID 2026 Busan, the 26th International Meeting on Information Display at BEXCO. Samsung Display brought a booth that reads like a materials science lecture you can walk through. 4 ideas stood out, and every one of them is really a story about molecules. Start with viewing angle. 2 panels sat side by side, labeled conventional and enhanced. Same image and a visibly different fall off as you step to the side. Angular emission is an optical cavity problem. The spacing between the reflective anode and the semi-transparent cathode decides which wavelengths interfere constructively and at what angle. Tune that cavity for on-axis brightness, and you pay for it in color shift off-axis. Correcting it without losing luminance is capping layer and transport stack work, not emitter work. Second, form factor. A stretchable panel under the name Dynamic OmniView. A vertical slidable display extending to 15.5 inches. An OLED turntable, an eye pendant, and a humanoid head with a curved OLED face rated from -40 to +85 degrees Celsius. None of this works with a backlight. OLED is self-emissive, so the whole stack is a few hundred nanometers of organic film on a flexible substrate. The limit is mechanical. Every one of these shapes strains the organic layers, and the thin film encapsulation that keeps water and oxygen out. Third, the gaming wall, where the color science lives. A 34-inch QHD quantum dot OLED at 360 Hz, and a 31.5-inch ultra-high-definition panel at the same refresh rate. Quantum dot OLED starts from blue OLED emission and down converts through red and green quantum dots. That emission is narrow band, roughly 20 to 30 nanometers full width at half maximum. Narrow emission places the primaries close to the spectral locus of the CIE 1931 diagram, which is what pushes coverage past 90% of BT 2020. Fourth, the car. A big hole display, where an opening is cut inside the active area so a physical control sits surrounded by working pixels. Round drive control panels. A cockpit built entirely from OLED surfaces. Automotive is the hardest qualification organic materials face. Wide thermal range, direct sunlight, and tens of thousands of hours without differential aging between the red, green, and blue sub-pixels. Here the specification that picks the winner is not efficiency. It is emitter lifetime. One note on emitter generations, because it explains the roadmap. First generation fluorescence, Tang and Van Slyke, 1987, caps internal quantum efficiency near 25%. Second generation phosphorescence, Baldo, Thompson, and Forrest, 1998, harvests all excitons and approaches 100. Third generation thermally activated delayed fluorescence, Adachi, 2012, does it without iridium. Fourth generation multi-resonant emitters, Hadakiyama, 2016, add narrow band color. Red and green are largely solved. Blue is still open. Displays are chemistry you can see. This video is brought to you by LUMORA, high-purity OLED stack materials, and LAMKO for scale-up and CRDMO projects.